So, a couple of things about electricity. One is it probably is the one of the harder things to learn because a lot of people you can't see it necessarily. So, part of my goal is to get you so you can actually see electricity. And hopefully by the end of class, you will be able to, because that's really instrumental for being able to diagnose or repair cars that have an electrical problem. Uh, it's also something that is really the foundation of every system we have on the car today. So whether it's your steering, your brakes, your climate control, your heating, air conditioning, your seat, everything, your windows, everything is coming down to electricity today. So if I don't understand electricity, I can't fix a transmission, I can't fix an engine, I can't fix the headlights, I can't do any of those things, the braking system, the suspension system, all these different systems we have in the car all share something in common. That's electricity. And so unlike a car that might have been built 50 years ago, that yes, it had an electrical system, it had a starting and charging system, it had headlights, it had a radio, but the brake system didn't rely on electricity. The suspension system didn't rely on electricity. The steering system didn't rely on electricity. The engine only needed electricity to run the ignition system and start, but nothing else. So my transmission didn't need any electricity. So over the last 50 years, technology has really evolved where now everything is really integrated for one and computer controlled by two, and computers equal electricity. So what we're going to do is we're going to start off with really the foundation of electricity, what it is. I have several exercises I'll be assigning to you, which are on paper exercises. They're actually in the form of a homework. So it says quiz, but there's no time limit on it. And where you're going to go and you're going to solve for the unknown as we start learning about the different types of circuits. And we're going to apply different rules. So we have a couple sets of rules that we're going to apply based on circuit design. And we also have some electrical rules we're going to use. So we're going to use Ohm's law and Watt's law for our electrical rules. And we're going to be looking at series circuit and parallel circuit design. And each of those has rules that we need to learn. And we're going to do some exercises based on that. So we're going to go through the basic electrical circuit. A lot of these, I use a light bulb. And I use a light bulb just because it's easy to conceptualize, but that could be a motor. It could be a solenoid. It could be a relay. It could be anything I want. It doesn't change really anything other than the amount of current that's flowing through it. So whether I'm talking about a window motor or a light bulb, my rules are all the same. So I don't want anyone going, man, why are we learning so much about light bulbs? Well, I'm just using a light bulb as a way of explaining a circuit. We also have the PFAT, which I will show you guys again today on our Canvas, that allows you to go in and build a circuit. So when you're doing the homework that I'm going to assign you, I don't care if you do it by solving the math or by going and building the circuit and taking a measurement to get the answer. I don't care where you get the answer from, because either way you're learning, and the object is to learn. So some people are, hey, I can do this in my head, no problem. Other ones are, hey, I don't get this. I'm not understanding it. I can't remember the formula. So by all means, at that point, let's go in and just build the circuit and test it, because again, that's going to help you understand it. I don't want anyone getting frustrated saying, man, I spent an hour and a half on one question. You shouldn't do that. If you can't remember the formula, go build the circuit. If you remember the formula and you want to make sure you're right, go build the circuit. So either way, and that's why it's a homework. There's no time limit on these. And I have a couple of these exercises. I have one for series circuit, one for parallel circuit, and one for what's called a series parallel circuit. So we're going to divide those. We're going to take those one at a time. So the goal is to break the electrical down to a level that you're able to remember it and understand it. So even though I teach electrical at the beginning of the class, we're going to use what we learn this week and next week throughout the class, except for we're going to do it through application, not memorization. So what I want is I want a bunch of students that can think and analyze and make decisions, not parrot answers back to me. If I wanted parrots, I'd go to the pet store. So because of that, I'll ask you the same thing different ways, because I want you to know it, not just recite back to me the answer that you think I want. And we do that with things all the time that we know. So for example, if I gave you a test on how to tie a shoe, I bet you everyone here would pass. At least I hope they would. I know some of you are probably wearing slip-ons, but you know, I'll take that into account. But yet there was a time in your life where learning to tie your shoe was the most difficult thing in the world. And hopefully no one had that stress and anxiety this morning getting dressed. So my goal
Can I ask one question?
What's that, Warren?
I got one question. When you say build the circuit, you're talking about the simulator. And
Yes.
the problem I've came across in a previous class to verify my findings, if you put a certain number in it, it wouldn't give you the right answers based on the math class. And like if you set a light bulb at a certain amps or voltage, it's limited to what it will.
Well, it's limited based on the numbers in the program, but I've never seen it give the wrong answer, because you're able to change the resistance of the bulb, you're able to change the voltage applied.
Right, it would get very close. It wouldn't be a wrong answer. It would be maybe a tenth off or something.
Oh, so you're talking like a rounding error where it might be right answer is 1.33333 forever, and it just gives you 1.3.
Right, you got it. So
yeah, so it will do some rounding errors like that. And I really don't, I'm not real concerned with that, because I think we still have the concept when that happens. But the other stuff, and I have very few questions that are not a whole number answer, because my goal is not to see, can you do math? My goal is, do you understand the concept? So I think that we can understand the concept using 3s and 4s and 6s and 2s, as opposed to a 0.006 and I just don't like to make things overly complicated, because I want us to understand how these pieces all fit together more than how hard can I make the math. And you'll see what I'm talking about as we get into this.
Thank you, sir. I just like looking at the numbers as in a range.
Right.
Yeah, and that's all I look at.
Yeah. So circuit function, we're going to talk about Ohm's law. I'm going to talk about circuit construction and what is a circuit. And what I mean by what is a circuit, what do I need in order to have a circuit that functions and doesn't catch on fire, doesn't melt down, and actually turns on when I want it on. We're going to do some circuit tracing exercises. So I will be sending out some PDFs that you can either download or display on your computer screen for some circuit tracing exercises we're going to be doing. And we'll be doing some circuit testing. We'll do voltage testing, voltage drop exercises. So again, I have some voltage drop exercises that I will send out a PDF file. And when I send, what I mean by send those out, I'll send out an announcement saying, here is the files for class tomorrow. So that way, if you can print them out, you want to print them out, that's fine. If you don't, I get it. You're not going to be turning them back into me. But it's there so that you have something other than the PowerPoint for me to go over with you and for you to go over with yourself as you study. We're going to talk about resistance testing and why the book is fundamentally wrong on how they tell us to do resistance testing and why it doesn't work. We're going to talk about continuity testing, and we're going to talk about current testing. And current testing is pretty high level. Because of Ohm's law, I can measure the current and get the resistance. So in other words, we have three things here, and I can use voltage to measure resistance, and I can use current to measure resistance. So I don't necessarily have to use an ohm meter to measure resistance. So I can measure resistance directly, or I can infer resistance measuring it indirectly. And what we do in industry is we measure it indirectly most of the time because it's more accurate and it's more efficient. In the auto industry, we get paid by the job, not by how long it takes us. And I only make money if I make good decisions. So the goal is to try to make a good decision quickly. So the relationship of voltage, current, and resistance. So voltage is the difference between the weight of water in the two containers. So voltage is pressure, is a way of thinking about voltage. The more voltage I have, the more pressure I have. Current is the amount of water flowing through the tubes. So that is how much is going, how fast is it going there. Resistance is the diameter of the tube. So if that tube is small, a small amount of water is going to go through it. So no matter how much voltage I have, I'm still going to be limited how much pressure I can put through the tube. That being said, we have, like a lot of you probably have, I have a water dispenser at the house, right? It has the 5-gallon jug on top and you open the spigot and let water out. Does the water come out a lot quicker when the jug's full than when the carafe is almost empty? Well, why is that? Because there's more pressure when the jug's full, right? There's more pressure. There's the weight of the water applying pressure. So the same thing's true with electricity. If I have more pressure, that means that even though it's going through the same hole, same restriction, I can flow more. Right? Think about your hose. If I crack open the garden hose just a little bit, not much comes out. But as I open up the faucet, more and more water is going to come out the same size of the hose. Because the restriction is what? The faucet. So the more I open the faucet, I have the same pressure on the other end, but I have more restriction when the faucet's barely open. So therefore, I'm going to get less current flow. As I open the faucet, I get more and more current flow. I have the same amount of pressure. I'm changing the resistance. So resistance and current flow are directly related to each other. So there's a lot of different ways they explain, try to explain this relationship. This is probably one of my favorites because we can kind of visualize it. And I'm going to come back to this picture when we start talking about parallel circuits. I'm going to remind you of this. So a parallel circuit would be if I have two tubes going between the two tanks, right? They're in parallel to each other. I have two tubes. A series circuit is what we have right here. One tube. Everything has to go through that one tube. So Ohm's law says I need 1 volt to push 1 amp of current through 1 ohm of resistance. So if any one value changes, it affects the others. So I can't just change one number. If I change one number, one of the other two numbers has to change. Now, they both can change, but in the case of voltage, normally voltage stays fairly constant, which means if I change resistance, I have to change current flow, or if I change current flow, resistance has to have changed. That's also why we see systems using more voltage. So cars have not always used 12 volts. In the mid-1950s, we went from 6-volt vehicles to 12-volt vehicles because a 12-volt vehicle can flow twice the current through the same amount of restriction, right? Because it has twice the pressure, which means what? I can run smaller cables. I can do so. It lightened cars up, made it cheaper, made it much more reliable. If I talk about a hybrid vehicle, hybrid vehicles, their battery packs are normally anywhere from about 140 volts up to close to 400 volts. Why do we use more voltage? Because I can do more work with less amperage. So I can apply that through. But the big thing is the resistance now is what? I'm going to flow a lot more current through the same amount of resistance. And that's where we get into safety. And that's why with hybrid vehicles or things like that, safety becomes a real concern because we're working with a higher voltage. So therefore that current's able to flow through resistance much easier. Just like the 110 in your house is more dangerous than the 12 volts on your car. So relationship of volts, amps, and ohms. And this is only for complete circuits. So this is only for wires that are attached. So a complete circuit, we'll find out, starts at battery positive and comes all the way around to battery negative. So there's a little circle. If you notice, I have volts, amps, and resistance. The book may have E over I times R. It's the same thing, except for we don't use E in auto, and I don't use I in auto. So why confuse you and give you an acronym that you have to translate to something we use? So myself and a lot of other instructors along with some publishers have moved into using volts times equals amps times resistance for the purpose of auto, because it makes sense. It's what we use, it's what our meters show. So volts equals amps times resistance. Well, if that's true, then amps equals volts divided by resistance. Or resistance equals volts divided by amps. And because of this, I could measure amps. And if I know the voltage and I know the current flow, I can figure out the resistance. So if I know the voltage and the resistance of a circuit, I know how much current it should flow.
Mr. Perrin, so
Yeah.
in this PowerPoint, it says volts, amps, and ohms. So the resistance is the ohms?
Resistance is the ohms.
Okay, thanks.
You bet. Yeah, so ohms is the unit of resistance that we measure, just like amps is the unit that we measure. So I could have put a C there for current, I guess, instead of A. But yeah, ohms is a measurement of resistance. And amps is a measurement of current. So I can solve for the unknown here. So here I have a pi, I have my, and sometimes you'll see this drawn as a triangle, but I have volts equals amps times resistance. So if I cover up any one of these, now I have volts divided by resistance will give me the amps. I can also take volts divided by amps will give me the resistance. Or I could take amps times resistance gives me the voltage. In this last one, this amps times resistance equals voltage is what allows me to use voltage to find resistance in electrical circuit. So if I have current flow and I have resistance in the middle of a circuit and I'm measuring before and after the resistance, I'm going to have a difference in voltage. If I have no resistance, but I have current flow, I won't have any voltage. So this is actually how we test for bad battery cables or bad wires or things like that. We don't use an ohm meter. We actually use Ohm's law in voltage. We measure for voltage, knowing if I have any voltage, while I have current flowing, there has to be resistance. Otherwise, there'd be no voltage. Because if I have water coming through a hose, the pressure is the same on both sides of the hose. But what happens if the hose gets kinked? Now, is there different pressure on one side of the hose than there is the other side of the kink?
Yes. Mm-hmm.
So if I had a meter to measure the difference between those two pressures, it would give me a number, wouldn't it? But yet, if that kink's gone, now that meter would say, hey, these two pressures are the same and would read 0. So that's how we're actually able to use voltage to measure resistance. And we'll get more into this. So a lot of, I don't want anyone concerned that they're, man, I'm not quite getting this at the moment. Because I'm just introducing things to you now. We're going to spend a lot more time on these, but I want to get your minds kind of thinking a little bit. So Ohm's law. So you see the EI and R in parentheses here. So volts equals amps times resistance. So if I have 12 volts times equals 0.2 amps times 60 ohms. Well, that's a lot of math. I prefer 12 volts equals 4 amps times 3 ohms. That I can remember. So most of my stuff is going to be in the more like the lower one. I don't like stuff where we got decimals and stuff, because then that turns it into a math class. I don't want to teach a math class. I want to teach an understanding of how the electrical circuit works. So for example, on my lower one, if my motor is 3 ohms, I should flow 4 amps. But if I measure it and I'm only flowing 2 amps, that would tell me what? There's high resistance in the circuit. I have a problem. That might be why my motor's going slow. So you can see how I can use one thing to figure out something else. So solving for the unknown value, 12 volts divided by 6 amps equals 2 ohms. 12 volts divided by 2 ohms equals 6 amps. And 12 volts equals 6 amps times 2 ohms. So with the exception of some of the exercises in the that we're going to do this week on series circuit, parallel circuit, and series parallel circuit, everything on tests, everything else in the class, my batteries are all 12 volts, and I use whole numbers. So again, why do I use 12 volts for a battery when a battery is, we'll find out, is really not 12 volts? It's because I want the math to be simple. And even though batteries aren't really 12 volts, 12 makes a much better number if we're doing math. So if a circuit has 12 volts applied to it and the resistance in the circuit is 12 ohms, what is the current flow?
1.
1, you got it. So again, not a hard math problem, but it shows me you understand the concept of what I'm talking about. I'm much more concerned with the concept than how hard I can make the math problem. Now, these questions, we're going to see them on a quiz when I get done with this PowerPoint, and I will turn a quiz on and you will see these same questions. So you're going to want to what? Write down questions and answers, or know you know it or something, because these are worth points when we're done with the PowerPoint. So this is what I was talking about.
Mr. Brian, excuse
Yes.
me. I have a question. So one of your slides says
Yeah,
it's for
answer भी मारो.
Hold on a
Sorry.
second. Go ahead.
Okay. So one of your slides says for complete circuit only.
Right.
Does that mean anything?
It does. It means a lot. And that was a good pickup. And we're going to actually explain what a complete circuit is here in the next couple of slides. But what a complete circuit is a circuit with current flowing through it. So I've started at my battery positive. I've gone through my wire, through what we call a load. Now, a load, as we'll see, can be a motor, it can be a light bulb, it can be any number of things. And then completed my path all the way back to ground. So a complete circuit has current flowing through it. If there's no current flowing through it, then I don't have a complete circuit, and Ohm's law is not going to apply. So for example, in your house, if you walk in and your house is dark, your light circuit is what's called an open circuit. It's not complete. When you turn the switch on and the light comes on, you now have a complete circuit, and Ohm's law applies. Does that help, Dale?
Yes, it sure does. Thanks.
You bet. And in person, everyone gets clickers that I get to see how everyone did, and I don't get to do that online, unfortunately. So amps and resistance, and this is something that people get turned around and backwards on. They try to make them both go up or both go down. So what I built here is a teeter-totter. and I have a fixed voltage in my teeter-totter. So with my fixed voltage, if amperage goes up, resistance has to have gone down. So in other words, less resistance is going to equal more current flow. On the other hand, if resistance goes up, current flow or amperage has to go down. The only way that resistance and current flow could both go up at the same time is if my voltage increases. In other words, I have a bigger triangle. The only way I can make everybody higher is get a bigger triangle. So with a fixed voltage, which we do on our 12-volt DC systems, basically, and by fixed voltage, I mean somewhere between 10.5 and 14.5 volts. It's going to vary. But with that fixed voltage, as resistance goes up, current flow has to go down. If current flow goes up, resistance has to go down. Okay, so that's, that is something that's going to happen. So this is really good to remember, because people, when they do these exercises, try to make both amperage and resistance go the same way, and they can't do that. They're diametrically opposed to each other. It's like putting my thumb over the end of a hose and saying more water comes out. Well, we know that's not true. I've created a restriction. Now the water's going to come out under, I'm going to have more pressure in the hose because I've created a restriction, but I'm not getting more water out. I'm restricting the amount of water coming out. So I'm going to have less flow. So hopefully the teeter-totter helps a little bit.
Yeah, it does. Yep.
So like I said, these are some of the things I do in my slides, where I draw and do these animations and do these other things. And I'm by no means an artist, but I try to convey an idea that's, sometimes hard to convey with words, especially when we're not all in a classroom together. So I try to put some of these things in different PowerPoints, as you'll see as we go throughout the class, to kind of convey some of the ideas I'm talking about. So if in a circuit, if resistance increases and voltage stays the same, what will happen to current flow?
Goes down.
It goes down. So number 2, it decrease.
Mm-hmm.
You got it. See, you all thought this was going to be hard.
I had a difficult time when I was reading the chapters. I guess sometimes I would have to take a break, because if I go all the way through, nothing sinks in. But
Yeah.
the way you explain it, and because there's so many terminologies to remember, the way you're explaining it now it's sinking in. So thank you.
You bet. And that's kind of what I was saying. The PowerPoints to me and our meetings are critically important to understanding. The book gives you the background so that when I'm talking about this stuff, things will kind of pop. Or if you're reading the book after we talk about this stuff, you're not going to feel as overwhelmed and lost. But yeah, we like to have about 10 names for everything in the auto business. You think I'm kidding?
Oh, you're not? Okay.
No. And we'll see that as we go through different systems, and it's horrible. And we see that even in the case of one manufacturer may have 5 names for the same thing. Now, fortunately, Ford doesn't make very many vehicles, so we hardly run into that, but So what is a circuit? Leading to the question that you had a little bit, Del, as far as a complete circuit. So a circuit is a path that electricity will flow, making its way from battery positive all the way to battery ground. So there's 2 different theories of electrical flow. One is from negative to positive. One is from positive to negative. They're not mutually exclusive, but one you can fix cars with and one you can't. So I teach the conventional theory. So when we use the PFAT site, you can click on conventional or electron theory, and it changes the direction. And it's basically the concept, are you looking at the rocket going into space, or are you looking at the thrust pushing against the ground? Electron theory is looking at the thrust. I'm looking at the rocket. So if I'm trying to fix a car, I can fix it using conventional theory. And at the end of the day, I'm just a dumb guy trying to fix cars. So also, when we get into wiring schematics and we look at wiring on vehicles, we find that we use wires for the power wires, and we use very few wires for the ground wires by comparison. So it makes sense to start at the battery, trace my circuit to my load, and then find its way to ground and back to the battery. So it just makes a lot more sense trying to fix cars. And years ago, I had a gentleman in a class I was teaching, and he was an electronics engineer, and he had taught at university in Baghdad. And nice guy. And I'm going through this. He goes, no, it's wrong. It's electron theory. I mean, he is a scientist. He is on it. Real smart guy. And I told him, I said, look, I'm not saying you're wrong. I understand. But here's how we fix cars. And after he went through the course with me, and a lot of back and forth, and he sat in the front row, and when we really had a lot of great discussions, and he came to me at the end and he goes, I understand why I had such a hard time trying to fix cars. You can't fix them with electron theory. You have to do it the way you said. So again, it's just a different point of view. One is an engineering design point of view. The other is, how do I fix the stupid broken car in front of me? Right? Two different things. So all circuits must contain the following components: a voltage supply. By voltage supply, I mean power and ground, right? Conductors. So conductors can be a fuse, they can be a wire, they can be the frame of my vehicle. And a load. And a load can be a light bulb, a motor, anything that's going to use that electricity that has resistance. So any kind of resistance is a load. So I only need those three things to have an operating circuit. If I take any of those things out, my circuit won't operate. So if I take away my voltage supply, nothing's going to work, right? I'm sure everyone's had a dead battery at one time or another. Nothing works. Someone's probably had a wire come apart or a loose wire. So if I don't have a conductor, it doesn't work. If I don't have a load device, resistance in the circuit, I'm just going to melt wires. We call that a short, or if we go to another building on campus, they call it welding.
There are relations between them.
Right. So I have to have all three of those. And then depending on the size of my voltage supply, depending on the size of my load, will dictate the amount of current flow. So if I put in more voltage, I can flow more current through the same size load, right? So if I have, for example, 12 volts through 3 ohms would be 4 amps. But what if I have 120 volts through that same 3 ohms? Now that'd be 40 amps. The size of the resistance hasn't changed, but the size of the force pushing against the resistance has. So I'm going to flow more amps through that same amount of resistance. So the load controls, kind of like a traffic officer, controls the current flow through the system. Where we have problems is when the conductors become a load. So that would be a bad connection. That would be corrosion. That'd be a damaged wire. Any of those things makes resistance, which instantly any resistance is a load, and that's going to affect the circuit function. But in order for my circuit to work right, I need to have all of those. If I don't have a load, the fuse blows. So the load is what keeps the fuse from blowing. Now, most circuits also contain a switch, but a switch is not required to have a functioning circuit. Now, what do you think a switch is? Do you think it's a voltage supply, a conductor, or a load?
Low?
No,
None of those.
no, it's a conductor.
Would you call it, you couldn't call it a control device?
It is a control device, but it's a conductor.
Okay, the current has to flow. Okay, got it.
Right.
There's
I
no
mean,
voltage drop on the switch, so therefore it's a conductor.
right. In a perfect world, there's no voltage drop. There is, all conductors are allowed a certain amount of minute voltage drop, both through a switch or through electrical connections or through wire, because there's always some resistance, but it's very, very small. So yeah, a switch would be best because if you think about it, if I build a circuit and I have a wire coming from the battery positive to a switch and another wire coming from the switch to the battery negative, and I close the switch, what's going to happen?
No
Current should
flow.
flow.
Right, a lot of current flow, and we're going to melt something, right?
Yes.
Because it's not a load. Does that help a little bit with my definition? Yeah.
Yes.
Right? I mean, if you're not sure about something, just substitute. Wait a minute. Could I power up the thing with a switch? Nope, I need a voltage supply, so it's not a voltage supply. We just proved it can't be a load, therefore it's best classified as a conductor. So a voltage supply. So a battery, storage device for electricity, and chapter 53, when we get to that, we'll learn about batteries. And then our alternator, which generates electricity. So I'm going to use my battery for starting the car. We use the alternator for running the car. So once the car starts, the battery is not the most positive or most negative part of the electrical system. The alternator is. So my circuit now starts at the alternator and ends at the alternator, not the battery, because it is the device that's generating electricity. If my car is sitting there and the engine's not running, then my circuit starts at the battery and goes back to the battery. So conductors, and I just listed some here: wiring, a connector, a fuse, a circuit breaker, which is normally self-resetting, so it's a fancy fuse. How about the engine and the transmission? They're conductors, big pieces of metal. Metal conducts electricity. The frame and body, more big pieces of metal that conduct electricity. A diode, which is a one-way street for electricity. And printed circuits. And I heard someone bring up control device computers. So on boards inside computers or on boards inside instrument clusters, they'll have what's called a printed circuit, where they actually put very, very thin conductive material onto plastic and allowed for the electricity to flow through that. So a load could be a light, a starter, a motor, a sensor, an fuel injector, an ignition coil, a solenoid or relay, or anything that is using the available power in the circuit. And if you notice what I put here, resistance in the circuit. So we use the term load and resistance back and forth a lot. So a circuit has two kinds of loads. It has what's called an intended load. That's the load that the engineers designed into the circuit. That's your motor, that's your light, that's your fuel injector. That's what the engineers designed to be there. And then we have what are called unintended loads. So an unintended load is a corroded connector. It's a melted wire. It's a loose connection. It's anything that is resistance in the circuit that the engineers did not originally design into the circuit. And so a lot of our diagnosis on circuits that don't work right is finding that unintended load or that unwanted resistance in the circuit. So keep in mind, I can have a load that's a light bulb, or I can have a load that's just a resistor. It's still a load. So any resistance can be a load. And again, there's other things listed. These lists are not all inclusive, but I wanted to give enough there for the idea of what I'm talking about. So a switch is a device that is able to complete or open a circuit. So one of the things that people really seem to struggle with is the concept of short and open. A lot of times when people have an electrical problem, the first thing they say is, oh, it's a short circuit. Well, let me tell you, we almost never have short circuits. Almost all of our electrical problems are either high resistance or an open circuit. So I'll use my hands. So right now my hands are open. They're not touching. So they can be this far apart and open or this far apart and open. They're still open, right? Not touching. Now they're touching with no load in between them. So that's a short. Okay, so here's open, here's shorted. In order to have a circuit that'll function properly, I need to what? Put resistance between my hands. Now I have my power and my ground, and I have a load, so I'm no longer shorted. No load, shorted. By having a load in between, I'm no longer shorted. There's something keeping the positive side and the negative side of the circuit apart. Does that help with that explanation?
Very clear.
I try, because I've spent,
Yes,
when I
sir.
first started trying to explain that, that was a 20-minute discussion.
Later on, will be electrical engineer.
Don't call him
I like
that.
the way how you
Short to
explain,
the
sir.
ground. Is that saying short to the ground or short to the ground?
Yeah, a short circuit means a circuit without a load. It's complete, but no load. It's shorted. Open circuit means we're not touching. So a switch can cause an open circuit, right? Because we've opened the switch. When I close the switch, I've completed the circuit. So if I have, say, my headlights stay on all the time, it could be caused by a shorted switch because the switch is what? Connected all the time. If my headlights never come on, it might be because I have an open in the circuit. It's now no longer complete or not able to complete. So switches are used in most circuits as a way to control circuit operation. So we think of switches like our light switch, which is becoming less and less of a switch, actually. It's more like a button to ask the computer to turn your lights on. But a switch could also be inside the computer. And we're seeing that more and more where they use transistors inside a computer to turn things on and off. So it's acting like a switch. So get out of your head that a switch is some toggle on the dash we're going to move up and down. Computers have all kinds of switches in them to turn things on and off.
I got one quick question to make sure I understand the short. Let's assume you test a switch and current is flowing open or closed. I would call that a short circuit.
Yeah, it's a shorted switch, not a short circuit, because you're still flowing through the ground and you're still flowing through the load and not blowing the fuse. So the circuit's not shorted because the light's
Right.
on all the time.
Right. Yeah.
The switch is
Like,
shorted because you can't open it.
thank you, sir. Makes sense.
You bet.
Mr. Brian,
Yeah.
so the amperage, it works the same for AC and DC current?
You asked, is the amperage the same for AC and DC?
Yes.
Okay. The rule that governs amperage is the same. Okay. So Ohm's law is the same. Now keep in mind, my AC current has what? 120 volts or 240 or whatever. So I have higher voltage, but yes, I can figure out my amperage the same way through resistance. It's the same exact principle.
Okay. It's just that, it came to my mind that, like for a starter, you use a heavy gauge wire for the starter, and usually, the wiring at home, it's thinner than the one
Right.
for starter.
Yeah, and the reason for that is because of Watt's law that I'll get to. And Watts is work. And watts is volts times amps. So as I increase voltage, I need less amperage to do the same work. And I've got some stuff coming up and we'll explain that and I'll break it down because we use, like, some fuel injectors are 48 volts, some fuel injectors are 95 or even 125 volts. Well, they're very high voltage, so they don't have to flow as many amps to do the same work. So we don't have these huge wires going to the fuel injectors. So I'll explain how that is and how the math works when we get to Watt's law. But yes, the rule on how we figure it is the same. But that's why we use a higher voltage in the house. That's why we have 220 circuits or I mean 240 or 480, when we start building bigger stuff, commercial stuff, because I can do more work using less amps, which means I don't need to run as big a wire.
Mr. Brian,
Uh-huh.
what is the difference between a manual or electric switches?
So a manual switch might be like a toggle switch or a momentary contact switch. An electric switch is something like a relay where we're actually using electromagnetism to open and close a switch, or a solenoid where we're using electromagnetism to open and close a switch, or a transistor, which is truly an electronic switch that we'd see inside a computer.
Okay. Thank you.
You bet. Yeah, one of my goals today is to try to get us kind of talking some of the same language, because I don't want to lose anyone. And the best way to do that is get us all talking the same language. So that's why I'm breaking down a switch, a load, all those things, is so that as we move forward, we're understanding each other.
Yeah, I like how you explain it because while reading the book, I don't understand anything.
Okay,
Thank you, Mr. Brian.
you bet.
Mr. Brian, I hope you don't mind saying in simple terms again the differences between the complete circuit, the short circuit, and open circuit. I still get confused somehow.
Okay, so a complete circuit has current flow. That's probably the easiest thing. So if current's able to flow, it's a complete circuit. An open circuit is a circuit that current cannot flow in.
And that means no touching, right?
No touching. A short circuit is a circuit that's connected without a load. So there's nothing to limit the amount of current flow.
Okay, so So an open circuit is a complete contrast with a complete circuit?
Right. So a complete circuit has current flow and an open circuit doesn't. So when I bring up which I will do today, I'll bring up the PFAT simulator that I have in Canvas, and I'll build a circuit and I'll show open, I'll show short, and I'll show normal, and you can see what I'm talking about.
Okay, doke. Thank you so much.
You bet. In order for a circuit to operate, it must have all the following except
In order for
Power supply.
Switch.
The
It doesn't need the
which
switch.
is the only thing I don't have to have, right? I could build a circuit that will operate
switch
without
and
a switch.
conductor.
Yes, switch.
It won't operate without a power supply. It won't operate without resistance because I'm just going to melt all the wires. And it won't operate without a conductor because I have no way of getting the power supply to the load, which is my resistance. But you see how I used a little different term here. I didn't put load, I put what? Resistance.
resistance.
You see how I did that? Because the idea isn't to confuse people. The idea is to understand that, hey, a load is resistance. I should be able to use those back and forth.
So load and resistance are the same.
All loads are the resistance of the circuit.
All
In a
loads
complete
are
circuit, all resistance creates a load.
all loads are resistance
Yeah.
of the circuit.
Yep.
Everything has resistance, right? Even conductors, semiconductors, everything has like a minimal amount of resistance.
Absolutely. And even wire, I have a meter that's sensitive enough. I can tell you the difference in resistance between a large wire and a small wire that are both the same length. So if I get down to that engineering level, everything has some resistance. We have an acceptable amount of resistance in our wiring switches and things like that are designed into the circuit. And then we have unacceptable amounts of resistance that create a problem. So that's the difference kind of between absolute, because you are absolutely right, and functionally correct. So 3 circuit types: series, 1 path for current flow. Right? What starts at positive is going to end at negative. One way to get there, no bypass, no nothing. If the bridge goes out, no one's moving. Parallel circuit, 2 or more paths for current to flow. So if one bridge goes out, it really doesn't affect the traffic on the other bridge.
So series is a positive to negative.
Yeah, I have 2 or more. I might have, for example, your fuel injectors on your car. If you have a 4-cylinder, you have 4 parallel circuits on an older vehicle.
How can somebody mute?
Yeah, I'm not sure who turned on. And then we have a series parallel circuit. So series parallel circuit is a little bit different, and then I'll have a load here and loads on each of my parallel paths. So even though you don't necessarily see the load here, each circuit will have a load in it. So if I drill down and look at my parallel circuit, it's really, in this picture, 2 series circuits next to each other. So in the series circuit part, the series circuit rules apply. In the parallel circuit part, the parallel circuit rules apply. So here in my series parallel, it's only a series parallel if I have a load in the series part of the circuit. And we only have a couple circuits on the car like that. One of which would be the dash lights on your dash, where it has a resistor to dim or brighten the dash lights. And then it has what? All the bulbs. So each bulb is its own parallel circuit. And then you have a resistor that controls the current flow through all the bulbs. So that's one of the few examples that we have on a car of a series parallel circuit. They're very rare. That's also why there's much less homework on series parallel. So what are the types of circuits found on the automobile?
All of the above.
All the above. Told you this would be a tough quiz today.
Oh, is this the quiz already?
Well, these are the questions you're going to get on the quiz after we're done with this PowerPoint. We aren't going to finish the PowerPoint today. We'll probably finish tomorrow.
For
Yep, number 4. So power and ground assumptions. Current flows in a complete circuit when there's electrical pressure, voltage differential. So what I've done here is I've taken a test light and I've connected between ground and a wire attached to the positive battery cable. So I've just made a circuit. So my circuit consists where my test light has a bulb in it, which is the load. One side went to ground and one side went to power. So I've just completed a circuit. So one of the reasons why we really don't use test lights anymore is because they make a circuit. And because I'm making a parallel circuit, it's going to change how things work, and it gets in the way with accurate testing. So this is a tool of yesterday that we really don't use anymore. And one of the reasons why is we make bad assumptions. So current flows in a complete circuit when there's a difference in electrical pressure or voltage. So here what I've done is I've gone between the 12 volts and I've put the ground side on my 5-volt sensor reference that comes out of the computer. Well, 5 volts isn't 0 volts, but yet my test light still lights up. Why? Because there's a difference between 5 and 12 volts. And my test light is able to complete a circuit and have current flow through it because of that difference. So it would lead me to a very potentially bad diagnostic where I have something that doesn't work right from a bad ground, but yet my test light thinks things are fine. So this just, again, really just is illustrating that a light bulb or a circuit can flow anytime there's a difference in pressure. It doesn't have to be from 0 to 12. It can be, as we see in this case, from 5 to 12, because that's still a difference. And these test lights are designed to work from 6 to 24 volts, which is why it lights up. But the key thing here is we don't want to assume something's ground, or we don't want to assume something's good power, which is why we don't use a test light, because if we assume things, we tend to make mistakes. And I wish someone had explained that to me 40 years ago. So series circuit has some rules, and you do need to know these rules. The first is that all available voltage is used. So in other words, if I start with 12 volts, when I get past my last load, I have to be at 0 volts. I have to have used it all. So it doesn't matter whether my load has 2 ohms of resistance or 2,000 ohms of resistance. It's still going to use all of that 12 volts if it's the only load in the circuit. So the amount of voltage doesn't change based on the size of the load in the circuit. Current flow does, but the voltage doesn't, and it has to use all of it. So the total resistance in the circuit is the sum or the total of all the resistances. So in other words, if I have resistance in my wire and resistance in my light switch and resistance in a connector and resistance in the load, all of that resistance equals the total resistance for the circuit. And every piece of that resistance is going to get some of that voltage.
Okay.
So you can't have anybody with resistance and current flow and not have voltage, because Ohm's law says voltage equals current flow times resistance. So if I have a complete circuit and I have current flowing through resistance, I will have a difference in voltage, meaning it's used some of my voltage. When I get to my last resistor or my last load, all my voltage has to be used. If it's not, the circuit's malfunctioning and I have another load or a bad connection or something I don't know about. So if I have a starter, for example, my starter needs to use what? All the voltage is going to less whatever's used by the cables and connections. If it's not using all of it, that would mean because maybe my starter has a bad connection somewhere. So maybe I have a corroded battery cable that has a lot of resistance. So now, instead of my starter getting 12 volts, maybe the battery cable is using 5 volts and my starter only gets 7. Or we've actually seen where the battery cable gets 11 volts and the starter gets 1 and doesn't work because the battery cable's bad. Because again, any resistance in the series circuit is going to take voltage. Because we only have one current path. Although I can have multiple loads, there's only one path for current. Does someone start to ask a question?
Yes. So like in order to measure that, like you test like the positive and then pretty much you go all the way down to the end of the series and you make the negative there to see how much voltage you have.
Yeah, and we're going to get to that when we get to chapter 53. which is our starting and charging. I'm gonna show you how to do a voltage drop test on the battery cable and show you exactly what's acceptable and how we do that. Yeah, you got the right idea. You're gonna put your voltmeter, one on the battery and one on the positive post of the battery of the starter, and crank the engine over, because I can only use Ohm's law in a complete circuit, right? So I have to be flowing current through it. Then I can measure the amount of voltage drop.
Thank you.
Yeah, good thinking ahead. I like it. And here's another key one. Because there's only one current path, current flow is the same everywhere in the circuit. So no matter where I test it, it's the same. So whether I test it on the positive side or the negative side, whether I test it closer to the battery or whether I test it closer to the load, as long as it's a series circuit, that current's going to be the same everywhere. That allows me to do testing at the easiest test point, at the easiest place to do it. So that is really kind of one of the tricks we use, is this rule of current is the same everywhere. So for example, if I want to test a fuel injector, I could dig out right inside the engine and find that fuel injector and put a tester on it to measure my current. Or I could measure it at the computer that might be much easier to get to, that's turning it on it, because the current's going to be the same both places. So should I test it at an easy spot or test it at a hard spot? Or
the
I can
resistance will not affect it.
what's that?
Different resistances will not affect the current flow.
Oh, different amounts of resistance will affect the current flow, absolutely. But the current is the same everywhere in the circuit. So it doesn't matter where the resistance is in the circuit, the current flow in the circuit's the same everywhere. So the resistance between two loads is the same at either side of the load. The whole circuit has the same current flow. So I can take it totally next level. And since my injectors use one wire for the power, and they use 6 different wires on my 6-cylinder for each of the grounds for 6 separate circuits, I can measure each of them individually to measure the current, or I could clamp on and just measure the current on the positive wire at the fuse or whatever that feeds all the injectors and measure them all with one connection. And since they should all have the same resistance, they should all flow the same current, right? So if I have one that flows much different current, I've just found my problem without taking anything apart. So where the book, and we'll see as when we get into the book, talks about using an ohm meter to ohm out the injectors, why would I? That's a lot of work. That's a lot of taking things apart. I would use current, and I would use Ohm's law here to measure current on all the injectors to see if I have a problem, and I can identify which one's bad. And I'll show you how to do that as we move in on the class. So a lot of what I do is, my motto is, how do I get the most information with the least amount of work? Because I don't get paid for taking customers' cars apart to see what's wrong. I get paid to diagnose customers' cars. And I do that by taking as few things apart as possible. Because anytime I take something apart, I risk breaking something or damaging something. So I want to be able to step back. I want to be able to run tests that are easy tests that give me a lot of information. And in order for that to work, I have to understand these series circuit rules. I have to understand not only these rules, but now how can I take Ohm's law, apply these rules to make up really cool tests and get great test results. So as we go through the class, as we learn about ignition systems, as we learn about fuel systems, as we learn about these different systems, we're going to apply what we're learning this week on those different testing. And so I'm setting the stage. I have a whole separate PowerPoint just on electrical testing, where I'm going to show how we go through and do some of this stuff. But I kind of want you guys thinking a little bit out of the box. You know, why would I take something completely apart to go in and do a test that didn't even work well 40 or 50 years ago today, when I have better tools and better knowledge? You know, if I knew what I knew now, I'd have been a lot better mechanic 30 years ago. You know, and a lot of stuff took me decades to learn, but I think that's also why I have my own PowerPoints here and not the books, because I've kind of tried to sort out what do I really need to know, what makes me money, what helps me fix a car, what helps me understand, versus all this other stuff that still confuses me sometimes to this day. That doesn't help me fix a car or doesn't help me understand what's going on. So I break a lot of systems down this way. So here's some schematic symbols, and we are going to be getting into schematics. So this is just a kind of a quick reference. But since I'm going to be using schematics to explain series circuits, I wanted to give you guys a little bit of exposure to some of the stuff instead of just throwing you in and expecting you to know it. And also I put this here as a reference for you. So I've got my battery, my fixed resistor, wires crossing that aren't connected. See, there's no bullet there. Wires crossing that are connected, a switch. Now, the interesting thing about switches are always drawn in schematics in their default or natural position. So this switch is drawn open. If it was drawn closed, that would mean the circuit's normally closed and you would have to activate the switch to open it. So the advantage of this is it shows me how the system was built and how it should work before I do something to it. So this is a variable resistor. You can see it's very similar to our fixed resistor. This has a line going through it. These are connectors, and they can be drawn either way. And these are drawn as a male and female connector. So when I go to the car and unplug it, I can tell which side of the connector goes which direction. And also you can see here, it's underlined, I have a C, and there should be numbers here other than zeros, but this connectors all have a number. So I can look up in a in a component locator and find out where that connector is on the car. I can also probably get a picture of what that connector looks like. Here is one of the two symbols we use for ground. And you can see this is a G200 ground. So the 200 tells me it's between the A and B pillar, or basically inside the passenger compartment between the firewall and the B pillar where you guys are getting the tags from. So that's where that ground connection is. So that's what that 200 tells me. Here's a splice, it's the middle wire, shielded wire. So the shielding is not part of the circuit. It is there to prevent electromagnetic interference to the circuit. This is a relay, and we'll spend a lot of time with relays. A relay is actually two circuits. One circuit is the load for one circuit, as we can see right here. These are resistors. And it's a switch for another circuit. So we asked about an electronic switch, right? So I'm going to use electricity to generate electromagnetic field, which will close the switch. So this is actually two circuits. And relays are neat because they allow us to use a small amount of current to control something really big. These are fusible links or fuses. We can see here our ground, our diode, which is our one way, and these are transistors. And one is a NPN, the other is a PNP, negative, positive, negative, or positive, negative, positive. And I don't care. I'm not going to make you learn that. I still can't keep them straight, and it doesn't affect me. I can still fix cars. So really all I care about is that you can recognize that it is a transistor, and a transistor is an electronic switch we'd see inside a module or a computer. So that's really all I really want you to know as far as on the schematic part of a transistor. I am not going to ask questions between PNP and NPN because I don't care. You want that, go take an electronics class because it doesn't help you fix a car. I know the book gets into it and stuff, but it's nothing I'm going to test you on.
Question, sir.
Yes.
What is diode? What's that diode?
What is what?
The last,
Diode.
oh, diode.
Diode.
Diode, yeah.
Oh, I'm sorry. I thought I said diode. So a diode is our one-way street. Electricity can go one way, but not the other. And you can see you have the two ground symbols. Kind of depends on which continent the wiring schematic was done on to which symbol you're going to get. So I'm going to stop share for a sec. Get out of PowerPoint. And we're going to get into series circuit. And once we do that, so I'm going to open up the series circuit assignment. I may open it up, but it won't be due till the end of the week because we probably want to go over stuff tomorrow before you try to do it. So I might not even open it till tomorrow morning. But I don't, if you're not comfortable with it, don't even try it till after we go through tomorrow's PowerPoint, but I will probably open it up today. So let me get out of that. Okay, I'm back to CDX. Okay, so if I go into modules and I scroll down, oops, went too far. Where is it? Module 1, module 2, and I have training resource reference right here, 2.1.8. So if I click on this, it brings up this right here. And you have an intro to lab. I'm going to just jump right into the lab. Now I have this set up to run in Canvas. So you don't need to go to a different website, don't have to find the right tab, any of those things. And since it runs in Canvas, it should also run on your phone. So I'm going to build a circuit real quick. So, and I'd like a 12 volt circuit. So I'm going to adjust this to 12 volts. And I need a conductor. And let's give it another conductor. Okay. So right now, this is an open circuit. Are we good with that?
Mm-hmm.
And I can tell there's no current flow. I'm going to go to conventional flow. Okay, so I have an open circuit. Now I'm going to make a short circuit.
That's cool.
Okay, short circuit. And I can actually measure my amperage here. That's a little high. All right, so let's get rid of the fire here. And let's put a load in my circuit. And let's go with a light bulb. I could use anything, but I'm going to use a light bulb here. And if I look at my light bulb, let's go down to 3 ohms. So 3 ohms. Now, how many amps should I read? 12 volts.
4
3
amps.
ohms is how many amps?
I'm sorry, say that again. I'm sorry.
If I have 12 volts in a circuit with 3 ohms of resistance, 4. And I can put this on and guess what? We're right. So now let's change the resistance here. What if I have 4 ohms of resistance? What's going to happen to current?
3.
Right, it's going to go down. And if I go to 6, now it's what? 2, right? If I could hit 6 here. Now I'm at 2. So you see, as I raise resistance, how do I get 60?
Say that again.
Lot less current flow, right?
Mm-hmm.
Bulb's not as bright either, is it? So, but yet I'm still using all my 12 volts, aren't I?
Yes.
So if I take a look here, and if I go from here, I'm at 12 volts, right? So watch what happens when I change my resistance. Am I still at 12 volts?
Yes.
So the amount of current flow is based on resistance. Voltage, my single load is still going to use all of my voltage. So this is a complete circuit. If I cut this, it's now an open circuit. So what's my current flow in an open circuit? Nothing, right?
Yeah.
Yeah, 0.
0.
0, right. Come on.
0.
So if I close the switch,
No current.
now I got current, right? I'm still dropping that, so I've completed the circuit. If I open the switch, current stops, doesn't it?
Mm-hmm.
Does this help a little bit? You can also draw it like a schematic.
So closed circuit is also a complete circuit.
I'm sorry, what a closed circuit is what?
Also complete circuit?
Yes, you got it. So so right here, I've built a nice circuit and I'm going to close it with a switch and now I'm flowing current.
Okay.
If I open the switch, I now have an open circuit.
Over here.
There's no current, there's no voltage.
Yeah. I still have voltage up here if I test there, right? So it's all about where you, oops, I don't want to cut that.
There's no
So
current.
now let me show you what happens if we have a resistance here. So say I have a bad connection. Now what happened?
Slow.
It's flowing and I'm what? Only 2 volts at my light bulb.
Yeah.
Because I have 10 ohms there. So I only have 1 amp of current. See, right? Because if I have my 10 ohms here and 2 ohms here, that's a total of 12 ohms. 12 volts divided by 12 ohms is 1 amp.
One.
But see, here's what's neat. I can test anywhere. See how that's the same everywhere?
Okay.
Yeah.
So I can test anywhere. I don't have to test at the light bulb. I don't have to test. I can test here at the battery, test here at the battery. I can test on the positive side. I can test on the negative side. I get the same result because in a series circuit, current flow is the same everywhere.
Everywhere. Okay.
So did this help a little bit, Dell, as far as drawing this out?
Yes, a little bit.
Yes.
So a circuit is actually made of just wires and voltage. Is that how you explain a
Yep.
circuit?
A circuit is a power supply, conductors, and a load.
Excuse me, Mr. Perrin.
Yeah.
In order to measure your amperage, don't you have to put your meter in the circuit? In other words, take apart the circuit, put your meter in the middle of it in order to get that amperage flow?
Okay, great question. So yes and no. So I do have a amp meter right here, and and you're right, I do, if I'm going to use an amp meter, I need to use it in series. Okay, and I'm going to flow through the meter. The issue with that is I'm limited to normally about 10 amps. What I'm using here is an inductive clamp. And since the electrons going through here create electromagnetic field, an inductive clamp on a meter is able to measure that and give me a number without breaking into the circuit. So with few exceptions, we really do not put an amp meter in series with the circuit anymore. We normally use an inductive clamp unless we're looking for very, very small numbers.
So when you were talking about the injectors and not taking it apart to measure resistance, in my mind, I was thinking that you have to take it apart in order to measure amperage, but you're saying by using this this different tool, that's why you don't have to take it apart.
Correct.
Otherwise you would, and there would be no advantage of measuring amperage over taking it apart and measuring resistance.
Right, and I might blow the $20 or $30 worth of fuses in my meter.
Let the factory smoke out.
Exactly. Where the advantage of this is that even if I bypass my load, kick this down to 0. Now, right, I've got a real problem here because I have no, so you can see I'm going to blow the fuse because the current's so high, but my inductive clamp's just going to say, hey, you're out of your limit.
Are inductive clamps AC or DC, or are they
Yes.
both?
Normally they're AC or DC. Normally they're different. I've not seen one that's both. Not saying they're not out there. I just have not seen one.
Now,
The ones I have are separate.
Mr. Brian,
Yeah.
can you get smaller clamps? I mean, when I visualized inductive clamp, it's usually a big thing you put on the battery cable. You know, I'm old school, so you can buy them smaller to fit into a multimeter.
Yeah. Let me see. Yes, wave. I should still be sharing my screen here. So I'm just going to AES Wave here, which is a website that carries a lot of stuff. And if I come in here to, let's see, lab scope accessories and current probes. Let's see what I get here. Come on. There we go. Oops. Hate that. So you can see, doggone it. Let me back up. So can everyone see this?
Yeah, we can.
Okay, so you can see the bigger ones, like here's a 600 amp clamp right here, Warren.
Yeah,
And then over
that's what I
here-
usually worked with.
Right, and over here you can see one that's a 60 amp. Oh, this one is AC and DC, so that answers your question. So you can use them AC and DC on some of these. So if I go in here now, I zoom the picture up. This is a picoscope one, but you can see they get fairly small.
Because you could easily wrap that around more than one wire, the
Yes.
bigger clamps, and that could really mess you up.
Right.
Meter reading.
Yeah, and see, so we have low range with banana clamps. So I bought some of these for the school. And these are a fraction of what the tool guys get for them. And it kind of shows the size.
So you'll be sending that out to us, right?
No.
We need to practice.
No, I hear you. Believe me, it was a lot of work going to online because I have all kinds of exercises for people to do in my class when we're in person. And I've spent a lot of leveraging to try to get equipment so that we could do this testing in person. And I'm not even allowed on campus to go do stuff. So
If it's only $1, maybe Brian can buy it for us.
yeah, this one's a little more than that. But you can see, and this plugs into your normal meter. So you can use this with any meter. This has banana plugs. And what it does is it uses a conversion here. So in this case, 10 millivolts or 10 millivolts to the amp or 100 millivolts to the amp. So these all have a conversion on them. So what you do is you put your DVOM or your DMM on volts, plug this into the volts, and you're reading millivolts, but it's actually amps. So it allows you, so it basically is sending a voltage out signal, even though it's measuring current. So it's changing that current into a voltage signal, which allows you to use it with any meter. So these are real universal. You can use them with any voltmeter. So they're pretty slick. And on that note, it's that time again already. So hopefully you guys were able to learn something in class today.